Hello and welcome to a discussion on rational functions and their graphs. So let's get started by looking at what a rational function is. It is the quotient of polynomial functions, where p of x in this case is a polynomial function and q of x is a polynomial function. It's very important to note, and please note that q of x is not equal to 0. The domain of a rational function is the set of all real numbers except the x values that make the denominator 0. For example, the domain of the rational function below, you take the separate pieces and you would set each equal to 0 and solve for the variable. So the domain is all real numbers except 0, 2, and negative 5 in this case, because those are what make that's in one case would make the whole denominator go to 0. Now, our domain for each of these, what we're going to do for these three examples is to take the denominator, in this case, for this first example of f of x equals 7x over x plus 20, we just take x plus 20, the denominator, and set it equal to 0, and then we're going to solve the equation. We may have to factor. So for this, all we have to do is subtract 20 on both sides of the equation. So we're going to have x is equal to a negative 20. So in this case, we can denote that the domain is everything except x does not equal negative 20. Okay, with number 2, we capture the denominator, which is x squared minus 64 equals 0. Let's add 64 to both sides of the equation, giving you x squared equals 64. Now to get rid of that x squared, do the square root property on both sides, so you're left with x equals a plus or minus 8. So that means that the denominator cannot equal a positive 8 or a negative 8. Okay, and finally, for number 3, x squared plus 7. Okay, notice that we have a subtraction right there. And we have an x squared. Anything x squared minus the x squared could give you, x squared minus anything could give you 0. When we have a plus and an x squared, that means anything squared is going to be positive. Adding anything that's not negative is going to give you anything that's positive. So this is all real numbers. It doesn't matter if you take the denominator and set equal to 0, you're going to get imaginary numbers, which means all real numbers within the domain of this function. Okay, because the denominator can never be 0. Let's look at finding vertical asymptotes if any of the graphs of the rational functions. Okay, for number 1, f of x equals x over x minus 4. For this, all you have to do is still capture the denominator and set it equal to 0 and solve for your variable. So for this, x minus 4 equals 0, just add 4 on both sides. And that simple step will give you the fact that x is equal to 4 in this case, so that is a vertical asymptote. For number 2, we have f of x equals x plus 4 over x times the quantity x plus 8. So we have actually x is going to be equal to 0, and we're also going to have x plus 8 equals 0. Right off the bat, we found that x was equal to 0, so for now all we do is subtract 8 on both sides, saying that x equals negative 8. So there are 2 vertical asymptotes for this one rational function. Okay, and number 3, f of x equals x over x squared plus 5. If you were to take x squared plus 5 equals 0, something similar that happened just a minute ago, there would be no vertical asymptote because x squared plus 5 can never equal 0. No vertical asymptotes. Because x squared plus 5 can never equal 0. So now we looked at vertical asymptotes, let's look at horizontal asymptotes. And the simple fact to work with horizontal asymptotes is just to take the coefficients of the shared variable, so there's an x squared here and an x squared on bottom. Just take the 25 over 5. Let's just capture that from the top part and say, since we're dealing with horizontal, it's going to be y equals, and 25 over 5 can be reduced to just y equals 5. Finally, for the number 2, f of x equals negative x squared plus 41 over 3x plus 4. Okay, we have an x on top and bottom. So we have negative 2 and 3. Let's just say y equals the negative 2 over 3. And it's just that simple.